In this video, we'll be covering different ways to manipulate the equilibrium constant. So sometimes the chemical reaction is written a certain way where um, if, let's say, the coefficients were multiplied by some integer, then you can also change the equilibrium constant based on what happened in the coefficients. So let's take a look at some ways that um, you can convert the equilibrium constant. So one way is if a reaction is written in reverse, then you basically just invert the the value of K, and we'll go over a quick example. Another way is if the coefficients change, then you actually take K to the exponent of what happened to the coefficients. And again, we'll take a look at an example. And also, if you're going to convert from Kc to Kp, there's a conversion you can do for if it's gas phase equilibrium. Okay, so let's look at some examples. If a reaction is written in reverse, you inverse the K for the forward reaction. So in other words, K reverse equals 1 over K forward. Okay, so here's the example. If we have N2O4 makes 2 moles of NO2, and K for this reaction is 0.212. If we have the following question, it says calculate K for, and I'm just going to write this same exact reaction in reverse. Then we get 1 over 0.212, and this would be 4.72 for, so the K value. So as you see, if the reaction is just, if it's just written in, it's just flip-flopped, then it makes sense that um, it's like if we write it this way and our K value is that low, then well, it favors the NO2 N2O4 side, right? So if this is still, remember, products over reactants. Now, if we just write the reaction in reverse, it should still favor this side, which it does. So now this number is greater than 1, so it favors the N2O4. So you're saying exactly the same thing by just taking the inverse here. So our next way is if you change the coefficients, then you raise the new K value to the exponent of whatever you changed the coefficients by. So this is better shown with a quick example. So if we have the following reaction, 3.8 times 10 to the fourth, and let's say we have this reaction. So it's the same thing, but the exponents have changed. Okay, so let's take a look and see what happened to this reaction. So this was a 1, and then it changed to a half. Up here it was a 3, and then here it's 3 halves. And for the ammonia, it was a 2, and then it became a 1. So it looks like all of these got divided by 2. So what we're going to do for our new K value then is we're going to go K new equals K old, and this is our old reaction. This is our new like converted reaction to the 1/2 power. So this would be 3.8 times 10 to the fourth to the 1/2 power, or square root. So this would be 190 I got. Okay, so there's one quick thing to mention before we convert from KP to KC or KC to KP is this concept of heterogeneous equilibrium. So solids and pure liquids are not included in equilibrium expressions. And I thought I'd mention this topic before we look at KP and KC. So you can solve for, remember, KC is with concentrations. So that would be in these brackets, the equilibrium amounts, which are in molarity, which is moles per liter, okay, over products over reactants. Now, Kp is going to be in partial pressure of your products divided by partial pressure of your reactants. So, partial pressure, if you remember, our units for pressure are going to be stuff like torr or ATM, stuff like that. So, I thought I'd mention this concept, heterogeneous equilibrium. It's when in your reaction you have more than one physical state. So we have gases and then you have a liquid. So this is heterogeneous. So more than one. Um, so this says write the equilibrium expression for the following two processes. So for this one, we do not include the H2O in the equilibrium. So this would be, if we wanted to write it in Kp, it would be the pressure of carbon monoxide divided by the partial pressure of CO2 times the partial pressure of H2. Okay, and if we wanted to do it in Kc, it would be the concentration of carbon monoxide over the concentration of CO2 times the concentration of H2. Now in this one, the tin, we see this solid, so that's not included in the equilibrium expression. So for this one, if you wanted to, if, for example, if the problem gave you pressures, you would want to do the problem like this. Most likely, if they're giving you pressures in kp, you would want to set it up using partial pressures. So you would go the partial pressure of CO2 squared over the partial pressure of SNO2 times the partial pressure of carbon monoxide squared, and that would be your expression. All right, so let's try our last example here. So now that we know that gases can be involved in equilibrium, we have this concept where you can convert between Kp and Kc, and this is based on the ideal gas law. So if we write out our ideal gas law, PV equals nRT. Now, if we solve for pressure, we get N over V times RT. And we see that pressure is directly related to the concentration. So we should be able to convert, but we just need to know what temperature the K value is being measured at. And then R will be our typical gas constant, 0.08206 liter atmosphere mole kelvins. But as you know, K values don't have units, so that's not going to be too important. So here's the formula. So it's Kp equals Kc times RT to the change in moles of, and this is only moles of gas. So let me write it different colors. So this right here is the change in moles of gas. So this is going to be the sum of the moles in your gas products minus the sum of all the mole, and these are found from the coefficients. These are from coefficients. So what you're going to want to do is look at the reaction and then hone in on the gases, so the substances that are in gas phase, and then count the moles on product and reactant side. All right, so let's look at an example. We'll just take a look at one. I mean, it's pretty straightforward as long as you count it correctly. Oh yeah, so if there is no, oh yeah, one important thing to note here. Let me use a different color. So if there is no change in moles, so if In other words, if delta n is 0, then Kp will equal Kc because this number will be 0, and then you'll be just taking RT to the 0 power, which is just 1. So RT to, or anything to the 0 power is 1. Okay, so Kp will equal Kc if that ever happens. I don't think that's going to happen in this one. So we have. Okay, so uh okay, so so Kc for this reaction would be actually, so this is a solid, so it doesn't count, and this is a solid, so it doesn't count. If you ever just have solids and liquids on the product side, then it's you just write 1 over whatever is on the reactant side. So it's going to be the concentration of O2 to the fifth power. Now, if you wanted to convert and write an expression for Kp, it would be this. It would be Kp would be Kc RT to the actually, so on your product side is 0 and your reactant side is 5, so it'd be 0 minus 5, so it'd be a negative 5 to the negative fifth power. So let's go to the next slide, and I have some examples for you guys to try. Okay, so go ahead and so this is the same reaction. So up here, this is the same reaction 3 times, and I just did a whole bunch of different things to these 3 reactions that are covered in the tutorial. So see if you could write the correct value for Kp in each case. Okay, so that's the end of our tutorial.